all of the scratch work that would be needed to justify to ourselves why it is that this subset of r star, the real numbers that are a rational multiple of the square root of 2 added to another rational number, why that subset of r star is in fact better than a subset. It's actually a subgroup. So let's go through the process of writing up that proof, just so that we can get some more practice with that before we take and look at our last topic for the day, which I want to look at some matrix groups and talk about the topics of center and centralizer as well. And it looks like my mouse is dying on me here. Sorry, give me a second. Everything has to go wrong at the same time here today. Okay. Great. So here's the proposition that we're going to try to prove. The subset H equals A plus B radical 2, where A and B are rational numbers and A and B are not both 0, is a subgroup of R star. All right, let's make sure that that shows up the way that we want it to here. Everything's a little bit slow. Okay. So the subgroup tests that we learn in this chapter, we can kind of think of those tests. Those are sort of, they're theorems, yes, but they also, for problems like this, can become part of our overall strategy for how we conduct a proof. So that would probably be the first thing I would signal to the reader. We'll use the one-step subgroup test. So that'll be the first observation that I make as part of my proof. That signals to the reader what my strategy is going to be. So now the reader knows, if they know what the one-step subgroup test is, what the burden of proof is going to be. And the one-step subgroup test begins with the universal quantifier for all x and y that are elements of my subset H. And so because of that, we need to eliminate that universal quantifier by using a let statement. Let x and y be elements of H. We must show, so now stating the burden of proof, we must show that xy inverse belongs to H. So that one line that I just wrote has the function of unpacking the one-step subgroup test for the reader, and therefore telling us again what the strategy is. Also giving x and y actual instances, eliminating the universal quantifier, which is part of that subgroup test's statement. And then also stating the burden of proof, that xy inverse belongs to H. Okay, since x belongs to H, we have that x is equal to, looking over at my napkin, x is equal to A plus B radical 2. So since x belongs to H, there exist rational numbers A and B. So A and B are rational numbers. Oops. Such that x is equal to A plus B radical 2. Similarly, since y belongs to H, there exist rational numbers C and D, such that y is equal to C plus D radical 2. So those are kind of the first two lines on my napkin, right? I know that x and y belong to H, and therefore I know specifically what form x and y take. They're rational numbers plus a rational multiple of the square root of 2. So now I've introduced A, B, C, and D into my universe by eliminating the existential quantifier. There exist rational numbers A and B. There exist rational numbers C and D. We also happen to know that A, B, C, and D are not all 0. Okay. So now let's do the calculation that we need to do. The calculation that happened over here on my napkin. So x divided by y, or in other words, x y inverse. Well, what we can do is we can do the calculation for y inverse. So note that y inverse is equal to, if I just take the a plus b radical 2 out of this process, y inverse is going to equal c minus d radical 2 over c squared minus 2d squared. So again, this is just the calculation that I would get just by rationalizing the denominator of 1 over c plus d radical 2. Right? But if I want to show why it is that this belongs to h, I could split that part that has the radical 2 apart from the part that doesn't. D over c squared minus 2d squared radical 2. And that's an element of h. So here we're kind of telling the reader, we're sort of giving away a little bit of surprise, right? That in fact the inverse property holds for h, because we can show that the inverse of y actually has the form rational number plus a rational multiple of the square root of 2. And therefore, now we'll do the calculation from the napkin. xy inverse is going to be a plus b radical 2 times that inverse that I just wrote down by the above calculation. So there's my byline. And then when I FOIL out that multiplication, I get this mess down here from the bottom of my second napkin, right? This whole big thing. So let's write that in. I want AC minus 2BD over C squared minus 2D squared plus BC minus AD over C squared minus 2D squared. It's radical 2. That's the line from the very bottom of my napkin. And then I just need to underscore to the reader why it is that we know that this belongs to H. And the reason is because both of these fractions, AC minus 2BD over C squared minus 2D squared, that fraction, as well as the other fraction, BC minus AD over C squared minus 2D squared, both of those fractions are rational numbers. And they're rational numbers because A, B, C, and D were rational numbers. This probably isn't going to fit on my screen. Let's find out. Yeah, it didn't quite fit on the screen. But we get the idea. Maybe because it didn't fit on the screen, let me just put this part down below the proof. And that meets our burden of proof, thus by the one-step subgroup test. H is a subgroup of R star. And that concludes our proof. Right. So again, what's the important part here? The important part is that we applied the one-step subgroup test to guarantee for us that H was a subgroup of R star. To do that, we picked an arbitrary element X and an arbitrary element Y, and our burden of proof is to show that X times the inverse of Y belongs to H. And the only real trick in this proof that required us to be a little bit clever was figure out why the inverse of Y was even an element of H to begin with. And so that's where we had to rationalize the denominator, this little step that we did over here on the napkin. That was the only way for us to really guarantee that our inverse, our Y inverse, was an element of H. And then once we did that, we could show that x times y inverse is then also an element of H. So secretly, if you look at the proof that I just wrote, I posed it as the one-step subgroup test, but this could also have been a two-step test. And the reason it could be the two-step test is I sort of separately verified that the inverse of y by itself belongs to H. So it really doesn't matter either way, whether you want to see this as a one-step test or whether you want to see it as a two-step test. Because they're logically equivalent, as long as we verify one of them, we have verified that H is a subgroup. So let's take another 15 seconds and pause, and then we'll come back and look at a matrix group example that will give us an opportunity to talk a little bit about the center and the centralizer of a group as well. But let's take a quick pause, and we'll come back and do that piece last. All right, so for our last set of problems for today, this is another example taken out of the Judson text, which asks us to consider a group of 2 by 2 matrices, where the operation in my group is addition. And they want us to prove that this subset of matrices, the subset of 2 by 2 matrices, whose trace is equal to 0, so A plus D is equal to 0, to prove that that subset is in fact a subgroup of G. So how are we going to do this? Once again, I'd like for us to think about using a subgroup test to get to where we're going on this problem. So for that, where did I put my pen is missing. Should rewind the video and go watch it back, figure out where I put it. Here it is. So for this, I again want to use a subgroup test to get to where we're going. And maybe since we already used a one-step test, let's use a different subgroup test for this example. How am I going to show that H is a subgroup of G, where G is the group of 2 by 2 matrices with the operation of addition? Can we use the finite subgroup test? And the answer to that is once again no, because A, B, C, and D here are presumably, it's not stated in the problem, but A, B, C, and D are all real numbers. And so there's infinitely many choices for each one of them. Therefore, H is definitely an infinite subset, so we can't use the finite subgroup test. Let's use the two-step test for this verification. So for the two-step test, we need to verify two things. For all x and y that are elements of my set, I need to show that x combined with y is an element of H, and also that the inverse of x is an element of H. And again, we have to carefully think about what xy means and about what x inverse means, because the operation in my group is the operation of addition. So this operation is, if I have two elements x and y, xy means to add the two matrices. The matrix x added to the matrix y. Right? So that's what the operation in my group means. So if I do that, what I want to show is that x plus y belongs to H. Similarly with inverse. So the inverse that's being spoken of here is the inverse with respect to the operation of addition. And so the inverse would be a matrix which, when I add it to x, gives me the identity. And the identity matrix, when the operation is addition, is the zero matrix. So the operation really does drive everything. X plus what is equal to the zero matrix, 0, 0, 0, 0. And we would conclude here that the missing link, the blank there, is filled in not by the inverse of the matrix with respect to matrix multiplication, but the inverse with respect to matrix addition, which would just be the opposite, just minus x. So does minus x belong to H? Would be what we would have to answer here. All right, so on our napkin, then we just have to figure out why this is the case. So if you've given me an x and you've given me a y, it means that x is a 2 by 2 matrix. Let's call it A, B, C, D. And we know that A plus D is equal to 0. It's a trace-free 2 by 2 matrix. Similarly for y, if I call it E, F, G, H, then those variables would have the property that E plus H would equal 0. And so now the question is, does x plus y belong to H? Well, what is x plus y? We'll just write it out. X plus y is going to be A plus E, B plus F, C plus G, D plus H. And this matrix will belong to H only if the trace of this matrix is equal to 0. In other words, if, when I add together its diagonal entries, if that result is equal to 0. So if I were to add those two, do I get 0? Well, if I add together A plus E with D plus H, I'm going to get A plus D plus E plus H. But by our assumptions about x and y, A plus D was 0, E plus H was 0, and so in fact we do get 0 plus 0 equal to 0. So that's my little napkin version of verifying that indeed when I combine x and y together with the operation of my group, xy belongs to H. That's 1/2 of my subgroup test. The other half is to verify that the inverse of x belongs to H. X is this matrix A, B, C, D, and A plus D is equal to 0. And therefore, minus x, that's minus A, minus B, minus C, minus D. That's going to belong to H only if its trace, the sum of its diagonal entries, is equal to 0. Is that true? Well, sure it's true, because minus A plus minus D is minus the quantity A plus D, but by assumption the quantity A plus D was equal to 0. And so minus the quantity A plus D will also be equal to 0. So there's my napkin version of this proof. Both of my elements of my one-step subgroup test have been verified. So now all that remains is to try and write up a more careful proof of this. Because there's matrices in this, I think I don't want to type this proof live, so let's just write this out as best we can here. So again, first thing that we'll do is we'll signal the use of the two-step subgroup test. We'll use the two-step subgroup test. And again, the two-step subgroup test begins with the universal statement for all x and y belonging to H. So we'll translate that into a let statement so that x and y have a meaning. Let x and y belonging to H be arbitrarily chosen. Our burden of proof. We must show that x plus y belongs to H, and also that the inverse of x, which we call minus x, belongs to H. Again, x plus y here and opposite of x here, because the operation in my group is addition of matrices, right? And so inverse means opposite, and operation means addition. And now because we have two things to show, we'll do the reader the favor of sort of setting apart each of those claims. X plus y belongs to H, colon. Wait, maybe before I do that, let's do as we did before and explicitly give x and y meaning. Since x belongs to H, there exist real numbers A, B, C, and D, such that x is equal to the matrix A, B, C, D, and a plus d is equal to 0. We do the same thing for y. Since y belongs to h, there exist real numbers e, f, g, and h. E, f, g, h, real numbers, such that y is equal to the matrix e, f, g, h, and e plus h is equal to 0. So now we've introduced x and y, and we've introduced the reader to a, b, c, d, e, f, g, and h, and told them something important about all of those numbers. Now we can return to our burden of proof. To show that x plus y belongs to h, x plus y, we'll do the calculation from the napkin. X plus y is a plus e, b plus f, c plus g, d plus h. That's a 2 by 2 matrix of real numbers. And the sum of the entries on the diagonal, a plus e added to d plus h, is equal to, when I trade places with the d and the e here, a plus d plus e plus h equals 0 plus 0 is equal to 0. Therefore, x plus y belongs to h. And then similarly, minus x is equal to minus a minus b minus c minus d, and minus a added to minus d is minus the quantity a plus d equals minus 0, which is equal to 0. So minus x belongs to h. And that meets my burden of proof, and we're done. So there's an application of the two-step subgroup test, right? To show that the set of 2 by 2 matrices with the operation of addition, the 2 by 2 matrices whose trace is equal to 0, forms a subgroup of the group of all 2 by 2 matrices of real numbers with the operation of addition. So there's the two-step subgroup test. I want to wrap up just by saying a few words about center and centralizer. So let's take a quick, again, one more 30-second break, and then we'll do an example of centers and centralizers, and we'll wrap up today's stream after that. Let's wrap up today's live stream by talking about centers and centralizers. If you watched my lecture videos, the way that I like to think about these concepts is to think about them as being the space in between abelian groups whose operations are commutative completely. Like every element can be interchanged with every other element in the order in which the operation is being applied, all the way to the other end of the spectrum where nothing commutes with anything, right? Where you can never interchange the order of multiplication. Centers and centralizers can tell us and quantify for us the space in between. The center of a group, G, is an answer to the question, what elements commute with everything? So the center of my group is going to be the elements that I can put them anywhere I want to in the line of multiplication, and the answer will always be the same. These are the elements that we can slide into any place in the product and not affect the value of that product. Meanwhile, the centralizer is a more restricted concept. Centralizer of an element, A, let's call it, in G. This is an answer to the question, what elements commute with A? What commutes with me is what I mean by centralizers. So the centralizer is going to consist, centralizer of A is going to consist of everything which I can slide past A and not change the value of my product. So, for example, let's take a look at the group D8. This is the group of symmetries of a regular octagon. So this is a fairly large group as groups go. Let's get up our tool in case we want to sort of graphically investigate some of these symmetries. This is our little Scratch app that we've been using to sort of shortcut our calculations in the dihedral group as soon as this thing figures itself out. And so the questions I want to answer while this thing is thinking is, what's the centralizer of R? R being my rotation. Turns out to be a 45-degree rotation when we're talking about the regular octagon, 360 divided by 8. Right? So there's the first question. The second question is, what's the center of the group? So the first question asks, what commutes with R? Right? What can I move to either side of R and get the same answer either way? The second question is, what commutes with everything? What elements in D8 can I put on either side of anything and not change the result? This is what I mean about streaming. Streaming from my office laptop is pretty, it kind of tends to slow everything down. This streams go much better from home lately. So while this thing is coming up, let's also write out the definitions of this. The centralizer of R, just to be specific about what I'm asking here. This is the set of all elements in my group that commute with R. In other words, Rx is equal to XR. That's what we mean by the centralizer of R. Right? These are all the elements which can be placed on either side of R without changing the answer. And the center is going to be the set of all elements in my group, such that for all G in D8, Gx is equal to Xg. So what I hope you can see from this example is that there's a relationship between center and centralizer. And the relationship is this. The center of a group is what we get if we take the intersection of all the group's centralizers. Your centralizer, my centralizer, his centralizer, her centralizer, all of them intersected together across all elements of the group. Intersect them all together, we get the center. So that's why when I say the centralizer is a more limited concept, if we intersect all the centralizers together, we get the center, that which commutes with absolutely everything. Okay, so thinking about the octagon in this example, we might ask a question like, does T belong to the centralizer of R? If T belonged to the centralizer of R, it would mean that RT gives me the same thing as TR, which it doesn't. I mean, we sort of knew that that wasn't the case, right? From the early times of studying the dihedral group, we knew that RT and TR are generally not going to be the same thing. So let me just write that down as an observation. Since RT is not equal to TR, this means that T does not belong to the centralizer of R. Right. Sometimes we write that with a subscript, sometimes we write it with parentheses. Parentheses are probably better. Okay. So T doesn't belong to the centralizer. On the other hand, R belongs to its own centralizer, because R is equal to R. Right? In fact, this is true for every element. Every element belongs to its own centralizer. Right? And we can extend that logic to convince ourselves that any power of R is also going to be a part of the centralizer of R. R squared is going to belong to the centralizer of R. R to the third power, R to the fourth power, and so on and so forth. And it's not too challenging to convince ourselves that those are the only examples. The identity r, r squared, r to the third, r to the fourth, r to the fifth, r to the sixth, r to the seventh. That is the centralizer of the element r in the dihedral group of the octagon. Sorry, I'm trying to slide my browser window off to the side here real quick, just so you can see everything. There we go. So the centralizer of r, that stuff that commutes with r, consists in this example of just the powers of r, just the rotations of this octagon, and nothing else. But what about the center of D8? What is there in the dihedral group of the octagon that commutes with everything in the dihedral group of the octagon? We know, for example, that r doesn't belong to the centralizer. Oh, sorry, to the center. Which, by the way, center is usually denoted with a Z. The German word for center starts with a Z, so ZD8 means the center of D8. R does not belong to that center because there exists an element which R doesn't commute with. For example, T. RT is not equal to TR. So because there's something that R doesn't commute with, that means that R doesn't belong to the center. It also means, for the same reason, that T doesn't belong to the center, right? Because T doesn't commute with R. And we can keep checking and checking and checking and checking. But it turns out that there is exactly one element besides the identity, which, by the way, the identity always belongs to the center, because the identity commutes with everything, always, in any group, because of the identity property, the two-sided identity property. So the identity always belongs. By the way, the center and the centralizer of a group or an element, respectively, these are always subgroups of the group that we're getting them from. And so for sure we know that they're going to meet the identity property, they're going to meet the inverse property, they're going to have the closure property, all of those wonderful things. Because they have the identity property, we know for sure that the identity element belongs in these groups, and we can verify directly. But it turns out that for the dihedral group of the octagon, there's one more example of an element that belongs to the center, that commutes with everything in my group. It's the 180-degree rotation, r to the fourth. Because we can check that for sure that 180-degree rotation commutes with r. So r to the fourth times r is equal to r times r to the fourth. This is certainly true because both of those things are equal to r to the fifth. But it's also true in the dihedral group of the octagon that r to the fourth commutes with t. How do we know that? Well, in the dihedral group of the octagon, RT is equal to TR inverse, right? But then that means, in particular, that if I were to take r to the fourth times t, that's r to the third times RT, and when I move this t to the left of that r, that's going to give me TR inverse. When I move that t one more step past one more of these r's, it's going to give me r squared times t times r to the minus 2. Every time I move a t from the right side of an r to the left side of an r, I get another r inverse coming out. So I'll have r times t r to the minus 3. I move it one more time, I get tr to the minus 4. But in the dihedral group of the octagon, where r to the 8th is equal to the identity, that means that r to the minus 4 is equal to r to the 4, and so I get tr to the 4th. And it turns out that because r to the 4th commutes with t and it commutes with r, and everything in this dihedral group being written as a product of t's and r's, that means that r to the 4th commutes with everything as well. So that means that r to the 4th belongs to the center. My 180-degree rotation belongs to the center of this group. So centers and centralizers are valuable for two reasons. One of them is that it gives us sort of very specifically a set of elements that we know we can slide to the left or to the right of other elements without changing the value of the element that we're talking about. And secondly, they also give us examples of subgroups of our given group. It's kind of a source of where we can get potentially interesting subgroups from. So that's going to wrap up our live stream for today. So sorry for some of the issues with the stream disconnecting and then reconnecting. That's just a work issued laptop being not quite as good at streaming as my PC is at home, so I apologize for that. I'm hoping that when this does get uploaded to YouTube, we can stitch it all together into one long video. But I hope this was useful. We're going to do another one of these live streams on Thursday of this week as we prepare for the exam on our first half of material for the semester. So I hope that I'll see you then.